I played maybe an hour for it.
Like this is Scott.
Oh my god, we didn't play Skyrim, so it's like
Okay, so pay attention to this class today, since I'm going to clarify several things. It's confusing you, frustrating you. Source transformation. Okay, I basically, to be honest with you guys, it's being used for Stevenings and Norton's equivalent circuit just for at the very beginning, right? So eventually you convert everything to either a current source and like this, or this. I've been doing this all the time, never see any problems. Just follow the method I taught in the class, right? And I've never used the source transformation, like whatever being put on the tutorial. But I was looking at the tutorial before I came to class. I was like, hey, let's just do it. It's just super simple. Ohm's law, right? Just divided by voltage divided by resistance or current source times resistance. You can keep converting and no problems. It's been nice by far, easy, right? Until I hit a wall this morning. So Storm visited. He was asking me to run through this, and I converted using the source transformation. So this is another lesson to learn. Whenever you don't know what you're doing, you always make a mistake because you don't know if that's right or no. It's just following whatever the tutorial told you to do. But the limitation is not documented. It didn't tell you like when you have a voltage source shorting these two networks, you shouldn't use source transformation. It doesn't work anymore. But it didn't tell you. So I found that out this morning. I never used it in the past. I probably won't use it in the future. Why? Why I have to use it? I've never used it, and it's been working perfectly, right? So, since I'm teaching you guys, so I need to let you know the limitations here. Okay? Let's follow, and we'll see what's going on here, okay? You got a voltage source and a resistor. You can convert it to a current source and resistor in parallel, no problem, right? Let's do it. I believe you have the same feeling, like why I use the method the professor taught in the class. Sometimes it works, sometimes it doesn't. Sometimes I can use this method, sometimes I cannot. Why? So you start hating circuits. What is this current source? What's the value here? 20 over 15K is 1.33 milliamps, if I'm right. Okay, so this divided by this, right? It's a 10K, it's 10 milliamps. Okay? So it's asking for IN. Remember, IN is called the short, IN equals ISC, right? It's basically just the Norton equivalent current. And in other circuits, so this is the original circuit. Before you do the transformation, like I said, here you have a voltage source, you'll see in a bit. So if you have a voltage source bridging these two terminals, you cannot do it to this, from here to here. I'm going to show you why, okay? So we have learned that, and it's working, no limitations on this, okay? If you have original circuit without any transformation or anything, no source transformation, just original circuit, fresh, original, okay? You draw a wire across these two terminals, and the current flows through this, it's going to be IN or ISC. So short circuit or Norton current. For sure, no limitations, okay? It's going to work always. So how to find this current? We have been learning, we have learned no voltage, mesh, whatever you have to use, okay? You should be able to find the current here, no problem, without any problems. All right, good. No source transformation. Draw a wire here, that's the definition. Why you draw a wire, that's the definition. Okay? So if you want to convert the original circuit to here, to the Norton equivalent, remember we have learned how to find out this resistor, right? We remove the load and looking backwards. No problem on that. Okay? So what about this current though? This current. So the way to find this current is short these two terminals and then just go through all the mesh, node, whatever you have to go through to find out the current here. This resistor is apparently this is getting shorted, so this is gone, right? For this case.
Sorry, is that the red line? Is that an imaginary wire that you drew, or is that something that you needed?
So when you are trying to convert this one to here to the Norton's equivalent, right? This is IN. The way to find out IN here is to draw a wire here and find a current. Yeah, it's an imaginary. It doesn't exist in the original circuit. You just drew a wire to help you find out the current through this wire will be the current here. That's something you need to memorize, okay? This is, according to the definition, that's Norton's equivalent. It's been working. No problem at all, without any issues. That's how you do it on the textbook or in the future on any exams, okay? Got it? Just 2 steps. From here to here, 2 steps. First step, remove the load and looking backwards. If it's the current source, disconnected. If it's the voltage source, shorted. And then find out the equivalent resistance, which is this guy. For this guy, draw a wire, get a current. It's gonna be this current. Done. Okay, good? For Norton's equivalent, that's it. No? Not getting that?
I mean, sometimes when, like, in the homework, like, you try to find the equivalent resistance just doing that method and it just doesn't work.
Let's try. So do you have a dependent source or no?
Yeah, even with just the independent sources.
Okay, let's try this one. For it's not asking for. Is this asking for? Oh, it's asking for RN. Let's try it. Let's try this one. Okay.
Well, that's what you were saying, right? It's fine. You find the equivalent resistance and then you use that to find the current. Is that what you were saying? Or no?
No. The resistance is not. You have all different methods to find out RN, RTH, right? Now we are talking about just the method from the original circuit to the Norton's equivalent. Okay, so I'm gonna grab another page to help you find out the RTH for now. Okay, RTH is RN, no problem on this. Okay, does that click at all? This is something we learned, right? So now let's try to find it. This is RN because it's Norton's resistance. Doesn't matter. It's going to be the same resistance. Okay, that's the original circuit, right? Disconnect and short. Short. $5K, $15K, $10K doesn't matter because it's getting shorted. Why? Because the ideal source has a zero internal resistance. So replace this one by wire and replace this one by disconnect circuit. So this is gone. This guy is gone, right? It's gone. And this current source is gone as well. So just ignore it. So far so good. This is getting shorted because when you're looking backwards, imagine you have a little current injected into this node. It's getting split. Whenever it reaches this point, it's not going through this resistor at all. It's gonna short it. So what's the final resistance? Just basically 15K times 5K over 20K. It's a 15K in parallel 5K, right? So what is it? 75 divided by 20. 75 divided by 20. 3.75. Okay. You'll never have any issues. This is the method I have used for over 10 years in teaching, including undergraduates. Oh, I didn't do homework in undergraduate. Teacher didn't teach. I hate my undergraduate education. No problem at all. It's gonna work always. Okay? RTH. Good. Now, let's come back for IN here. Don't transform to using any source transformation stuff. just use the original circuit, find IN, you'll be fine. So it's asking for IN, right? It's this problem asking for IN. But however, it's asking you to use. Oh, it didn't let you use source transformation. Just asking for IN. Okay. Yeah. So if you want to do that, that'll be even easier. Because it's been working, you just do whatever mesh or node, just find out this current. And this is getting shorted. So it's gone. If you draw a current here, yeah, this guy still exists. It's still there over there. Yeah, but if you do a mesh, let's do it. Don't want to skip too many things. Let's do it. This is gone because it's getting shorted. I drew a wire here. Make sense? Okay? So far so good. 10 milli, 10K, 20 volts, 15K, 5 milli, and this is IN. Alright? Let's find out which method we can use. We know this is 20 volts, right? And we know this is ground. Why? Because it's grounded. Alright, what can we do here? 20 volts, what's the current here? 2 what? 2 milliamps. Make sense? 20 volts, no problem, it's given. What's the current here? What's the current here? Mm-hmm. A milliamps and what's next? So that's 0 volts. What's the current here though? 20 over 15, right? Is it? A 20 volts drop. This is getting shorted because we drew a wire. Is it? 20 volts drop? Agree with that? So what's the current though? I hope I'm right here. It's 20 over 15K, 1.33 milliamps. All right. So this is not, this doesn't matter anymore. You know why? Did you see that? Does it still matter? What do we really care? KCL, right? What do you care? What do you really care? KCL. You already have the current here and here, so you can definitely find out the current here. Do we really care about whatever doing by this guy? Why do you still have to care? You already know the current here by the voltage. So what is the current here left? 1 getting in, 2 flowing out. So what's the current? Make sense? Without any problems. So what's the conclusion? These two things is not affecting anything over here or to the load. Why? Starting look at this point. 20 volts. Can you change the voltage here? If you operate the circuit properly, for example, don't short it, don't burn it. Is this one changing the voltage across these 2 terminals? No, it's ideal source. I already told you at the very beginning of the semester, if it's telling you it's rated as 20 volts, it's going to be 20 volts always. You just have to trust it. Like the current source. If it's telling you it's 5 milliamps, it's going to be 5 milliamps. It didn't tell you the voltage here, so don't know. So don't assume the voltage across it if it doesn't tell you. So the voltage is not changing. If you short it, here it becomes 0 volts. And the voltage drop is not changing, so the current is not changing. So whatever these guys, you can have a like 20,000 volts thing, doesn't matter. Have 100 amps current, doesn't matter. Because you are always getting 1.33 milliamps. And this is also defined. So this current is not changing.
So when you short it, is it you get rid of that 5K resistor?
Yes.
Because it's 0 volts at that.
Yes, because it's so if you it's called shorted. That's why it's called shorted, right? If you put a wire in parallel with this resistor, it's getting shorted. So you got a question: why the current source is not getting shorted? Because still impacting the circuit, still drawing current. It's an ideal. It's a source. It's not like a passive component. You can short it, right? This is a source. It tells you it's gonna pull 5 milliamps in this branch, so you cannot ignore it. Otherwise, you are get rid of the impact from the other branch. The resistor is just a passive component. You short it, you short it. Another way to think about it is, if you drew a wire here and you got a resistor, can you calculate the combined resistance? It's a parallel resistor. A wire is also a resistor with 0 ohms. Right? So a wire and a parallel resistor, you can combine them. How do you combine them? 0 times 5K over 0 plus 5K. That's the parallel resistance. What is the resistance? 0. So a wire in parallel with a resistor, you can combine it. Did I teach you anything about a wire in parallel with the current source? Is there any way to get a combined wire? No, we don't know how to do it. We shouldn't. It's a source. Okay? See the limitation here? Oh, we haven't reached the limitation yet. So see the perfect methods that I just introduced? It's been working for my whole life. Okay? No problems at all. If you use this method, it's gonna work. It's gonna work. All right, Norton's equivalent. How do you find out the Norton's equivalent? Just two steps, right? First, find out Rn, disconnect, remove the load, and looking back, short the current voltage source and disconnect the current source. Find out the resistance, and how to find IN. Draw a wire, and the current flows through it. It's gonna be IN. We just got it, and they are both correct. So now let's look at the source transformation. That's why it's not giving us the right answer here. Let me just label since I'm printing. This is bad, okay? Bad. Source transformation. Here, transform it. Current source resistance. Okay? According to the tutorial, it should be a current source and resistor in parallel. Now we look at the circuit. You are thinking, hey, Dr. Lee just taught me. Short it, and it's gonna be IN. Is that true? Now let's see. Resistor in parallel, combined, shorted. They're all gone, right? All the parallel resistors are gone. What are left? All the current source. That makes things super easy to find out IN. You just got several current sources, merge them, then you get IN instead of doing this. Are you getting the correct current? Let's see. You got 10 milliamps going up. You got a 1.33 milliamps going up. You got another 5 milliamps going down. So it's 10 milli, 1.33 milli, and a 5 milli. So you are trying to combine all these current sources so you know what's the current flowing there, which is exactly IN. What is the combined or effective current? merged. 2 going up is what? 11.33. 1 going down is what? 11.33 minus 5. It's giving you 6.33 going up. Going up to where? To here. No, it doesn't match. It doesn't match. We just got here, and I told you this is gonna always work. It's been working for my whole life. So the current of IN must be negative 3.67 milliamps. No doubt on that. However, we are getting 6.33 milliamps instead of the correct answer. Why? Because we did the source transformation at the very beginning. We get rid of the voltage source. It's changing the nature of the circuit. So start to hate circuit 1 even more. When should I do the source transformation? When shouldn't? Right? If you don't know what to do, just use whatever I just told you. It's gonna be working, always. Just use the original circuit. Don't do source transformation. If you change the sources, the type of sources, depending on how they are connected to the circuit, you are changing the nature of the circuit. And you are seeing issues. Always. So what's the conclusion? Could anyone tell me the conclusion? What is it? You want to take? What's that?
Do that one.
Yeah. Oh, use this one.
Yeah.
Yeah. Another conclusion. Be careful about source transformation. It's changing the nature of the circuit. What's that?
Can't do it in the middle. It has to be
You can do it in the middle. Yeah. That's another good point. Yes. What's that?
Can't you not do source transformation with the voltage source because it's not directly in series with the resistor?
You mean here?
Yeah.
I don't know yet, but sounds like that's correct. It could be. But we learn from this, right? At least we know how to get the right answer. And be careful about source transformation in the future, okay? Another thing I want to introduce. How did I know this is not working? After a student visited, I verified using another gold method that I know. I know it's going to always be working. Not circuit simulation. I'm better than that. I have the simulator, I have the tools, I simulate it. If I'm not seeing the correct results, I simulate it. Just to verify how stupid I am. But another way that I can verify, this is something I have to introduce because this is the very last problem in homework 5. And I'm telling students, this is my favorite method in circuit analysis. And a lot of people just ignore it. Why it's important? Because in the future, you are dealing with op-amps and other circuits, you will always be using superposition. I rarely use Thevenins and Nortons in real life, but superposition, always. It's been, even you get into the graduate level circuit classes, you always think about the circuits from the superpositions angle, you can always get things right. Important. Just make long story short. Okay, how do we do it? You're like, hey, Dr. Lee, you are introducing a new concept today before the midterm. It's good. Let's just introduce a really simple model here. So I'm asking you, what's the voltage here? What are the methods you have learned to find out the voltage? You have 2 voltages. Let's just put in the numbers. 1 volt, 2 volts, 1K, 1K. What are the methods you have used? KVL, right? KVL, it works. Just one mesh, right? It doesn't matter. So starting from here, you see a negative sign. So minus 1 volt plus I times 1K, right? Times 1K plus I times 1K again plus 2 volts. It's giving you 0. You can definitely find out what I is. What is I? So this is giving you I times 2K equals negative 1 volt So I equals negative 0.5 milliamps. That's the I in the clockwise direction. It's negative 0.5 milliamps. Okay, let's verify it real quick. So if I have negative 0.5 milliamps flowing through this resistor from here to here, so what's the drop from here to here? Negative 0.5 volts from here to here. Same voltage. I got a current flowing from top to bottom, which is also negative 0.5 milliamps. What's the voltage drop from here to here? Another negative 0.5 volts. Okay? What's the original voltage at this point? 1 volt. So 1 volt being dropped by 2.5 volts is giving you what? No. 2 negative half volts. So 1 volts. So see here, we just verified, right? So we are trying to verify it. Here from bottom to top, it's dropping negative 0.5 volts. And from here to here, it's dropping negative 0.5 volts as well because the current, we calculate the current using KVL, right? So 1 volt is dropping what? 2.5 volts, negative 2.5 volts. What is that? What's the voltage? 2. Are we getting 2 volts here? Is that 2 volts? Yeah, it's just 2 volts. Verified, right? The voltage source defines it. It's 2 volts. Verified. Okay, that's how we calculate it before we learn superposition, right? That's one of the methods you can use. If you use superposition, you involve one source at a time, or engage, whatever. Let's use involve. One source at a time. That's step 1. And step 2, for other sources, you either, for voltage source, you short it. For current source, you disconnect it. That's how we do, how we use superposition. So for this case, we look at each source at a time. Same circuit, right? Looking at each source at a time. So if we just look at, like, for example, we label it V1 and V2. So we do this, V1 only. When it's V1, there's V1 only. We keep V1 in there. And V2, we short it to ground. Find out the voltage. It's plus minus to the ground, compared to the ground. Okay, V1 only, so V2 is shorted. Why? Because the ideal voltage source has a internal resistance 0, so we short it. So what is V out? It's a voltage divider. It's 1 volt times 1K over 1K plus 1K, which is what? 0.5 volts. Okay, so this is V1's impact to V out. V2 only. Keep V2 here. 2 volts. Oh, where? Short V1 because we are not looking at V1 for now. Here's still VO. Let's do VO1, VO2. Right? So there are 2 VOs, 2 V outs, plus minus compared to ground as well. So it's not changing the polarity. So what is VO2? What is VO2? It's 2 volts times 1K over 1K plus 1K, which is 1 volt. Right? Okay? Then you have another, the third time, you do the overall V out equals V out 1 plus V out 2, which is 0.5 volts plus 1 volt, which is 1.5 volts. So you superimpose.
Why are the resistance? Why are they in series and not, or why are they in parallel, not series?
Wires are in parallel,
You
not
did
in.
1K over 1K plus 1K.
Oh,
Why
yeah.
are they not just add?
It's in series, right? That's one circuit. It's so ground. I didn't draw it, but actually ground is just one wire. If you have the same symbol here, it's one wire. So it's pushing current in one loop.
Okay. Why don't you add them? Why won't you add them?
Why don't I add them?
Yeah. Why isn't it just 2K if they're in series?
Oh, because in series is 2K overall, right? So basically this is the voltage divider equation I've been using, but you can also look at this equation from this perspective, which is 2 volts divided by 2K. It's giving you the overall current flowing that way, right? That's the overall voltage, 2K. That's the overall resistance. So you are getting 2 volts divided by 2K is giving you the current. Okay, and that current times this resistance will give you the voltage drop, which is exactly VO2. Okay, that's just a simplified way to look at the voltage over here. So you have, it's a voltage divider equation. I've been using this all the time. Let's repeat it so you can just feel comfortable to use it in the future. Okay, here's V out, like this. Apply voltage divider theory. What is V out? Same current. V out equals V in times this output resistor, which is R2, over R1 plus R2. Remember this. If you understand it, memorize it. In the future, just directly apply it. So see here, it's the same thing. You got the 2 resistors, and this is the output node. Or consider it as the output node. What's that? Multiply by 1 resistance. What? Multiply by 1 resistance, because we are trying to get a voltage drop just over this resistor. And we are trying to find a voltage here. So the voltage here is exactly the voltage across this resistor. That's why the overall current times here. Right? Any questions? Other questions? Are good? Use this, okay? Often. Always use this. Important. So we do this, we got a V out, use the voltage divider equation, find out the V out 1. And here, voltage divider equation the other way, find out V out 2. Then the overall V out will be this. That's how you superimpose the 2 results to 1 to find out the final voltage. That's called superposition. It's always working, okay? It doesn't like source transformation. It's always working. It's good. Make sense? Now let's, oh, this is already page 1, 2, 3, 4, 5 already. Let's come back to this problem. Come back to this problem. Why do we come back to this problem? Since I hate it. I should love it since it tells me new things. Let me know the limitation of source transformation. Always use the method that you know it will always work to verify something new, okay? Can we do superposition with this guy? What's the voltage source? Is that 20 volts? I don't remember it. 20 volts. 5 milliamps. No, 10 milliamps. 10K. Okay, let's do a superposition here. This is a problem that we did at the very beginning of the class, where we introduced the limitations for this for using transformation. Remember, and now we use a different method to solve it. Superposition. Okay, let's label this as V out. Let's deal with individual sources. Okay, let's start with this current. Let's call it I1, V1, I2. Okay, let's do it. I1 only. Let's see what I1 does to the circuit. No transformation. No transformation. Okay. What do we do with the voltage source? If we only look at I1 only, all the other sources should be either shorted if it's a voltage source or disconnected if it's a current source, right? So we only analyze one source at a time. So this time we are looking at I1, so all the rest of the sources should be either shorted or disconnected depending on it's a voltage source or current source. Make sense? So what should we do to this guy? Come on, guys. What's short? Okay. 15K. Current source, disconnect. 5K. All right. Now you got VO1. Are you getting anything? This current source works so hard, right? Getting some current flowing in here. Still happy? Still happy? Ooh, there's a shortcut. Let's just go through this path. Don't do anything to the rest. Like taking drugs, right? So good. Getting addicted to that short circuit. Never do anything else. It's a bad example, I'm sorry. Nothing else. Is there any impact to VL1? Okay? So this got verified one more time. Remember? Did we verify that same thing at the very beginning of the class? Let's look at it. Oh, here. Here, remember when we were here at page 2? When we got here, okay? We're looking at, hey, this one, 20 volts, 0 volts, current for sure, no problem. The current is not changing. 20 volts, nobody is changing that 20 volts. Okay? So I got a 20 volts for sure, I got a current for sure, nothing is gonna change it. So this guy is not doing anything to the following circuit. We had the same conclusion at the very beginning of class. Is this guy doing anything? How do you tell? How could you tell if this is doing anything? Let's look at the current. See if this guy is injecting any current to it. Oh, this is trying to inject 8 milliamps current to it. Is this getting 8 milliamps? Let's see. 20 volts. The problem tells me it's 20 volts. Okay? I have to trust it. 20 volts, 20 volts. So what's the current flowing through it? For sure. What's the current? 20 volts divided by 10K, 2 milliamps, no problem. Okay, for sure, okay, for sure. 10 milliamps, for sure. It tells me it's 10 milliamps, I have to trust it. It's an ideal source. 10 milliamps, 2 milliamps, for sure. So it has to be 8 milliamps, for sure. So this wire is having 8 milliamps. Okay, for sure. However, this is not reaching here at all. Why? 20 volts, 0 volts, it's always 1.33 milliamps. This guy is not doing anything. So where does this go? Where does this go? Yeah, why? Ideal source has 0 internal resistance. Even though we are not doing superposition, you should still know that. Whenever the current reaches here, it sees a short circuit. It directly goes down and go back to ground. The loop is basically like this guy is looping current back to itself. It's like a kid eating chocolates, right? This is a better example. Don't want to stop, right? Give me more chocolates. So always coming back. What's that?
Can we go for question 5?
Yeah. Oh, this is done? Are we done with this one? Have 8 minutes left?
We may not be.
Okay. But you don't need more? Okay, cool. But this covers superposition, right? This covers superposition, which is very last problem of homework 5. So which one did you say?
Question 5.
Question 5. So what's the number of the problem?
4.87.
Oh, yeah. So we did this in class. Refer back to the notes. So before I run out of time, I just want to give you an overall big picture of that problem first, okay? So I did that on Friday. Here. Follow that, will give you the right answer. Okay? So the first question is asking for the RTH. Yeah, RTH. How to find RTH? How to find RTH? Method 1, the method I introduced on Friday, is you remove the load. That's always the first step. Remove the load, and then connect a little testing source. It could be a voltage source, could be a current source. Doesn't matter if you follow tutorials. Sometimes it tells you assume a 1 volt testing voltage or assume a 1 amp testing current. Will confuse you a lot. Let's don't do that. Okay. Let's just assume it's IT and VT. Who cares? Just VT and IT. You can assume 1 amp. I can assume it's 100 amps. So let's don't assume anything. Just IT. Okay. IT and VT. So the goal is if you connect a little voltage source, and it's gonna inject the current into the circuit from the output. So it's injecting back like this one. It's injecting backwards. Okay. So eventually, if you can find out, you're treating everything here as a black box. Okay. You don't really care what's really inside. And if you can find out VT over IT, it's a testing voltage. Will give you a testing current. And the ratio becomes the resistance of the internal resistance of the black box. So the goal becomes to find out VT over IT. Okay, since you are trying to calculate the internal resistance of the black box, so the ideal sources still has to be either shorted or disconnected, but not the dependent source. The dependent source can be a lot of other things. They are not having like infinite internal resistance like current sources or like 0 resistance like the voltage sources. You don't know what's inside. It could be a current control voltage source like a transistors or something else. It's not a standard resistance. So you are not supposed to remove any of the dependent sources. However, for this guy, you should short it. This is the ideal source, short it when you are trying to find out the RTH. So if you short it, this voltage becomes 0, right? Here's 0 volts. That's why you use 0 volts minus V1 to find out the current. Okay, just keep moving forward to find out, list all the KVL equations and Ohm's law equations, just as what I did during the lecture. And do the substitutions. The goal, keep in mind. Yeah, what's up?
Can you say again why it's 0 volts minus V1 over 2 for I delta and not V1?
Because this is shorted. You replace it with a wire because it's 0 internal resistance. We verified that one more time with the other problem, remember? So if you have a voltage source bridging the two terminals, anything in front of it is not impacting the circuit. Why? It's like it's shorting everything in front of it, right? Okay. So
Yeah, so now there'll be an RTH, the power in question 2 on that one is fine.
yeah. So okay, let's get into that. So following this, you can find out VT over IT. It's already documented. You can definitely do that. For the maximum power delivered to this guy, it's a trap. I answered that question during online from online forum. Some students asked that question and answered that last week actually. So what's really happening? Let me see if you guys can follow. Okay. It's another limitation for equivalent circuits. So you probably are trying to use 50%, right? Because whenever R out, because it's adjustable resistor, right? So based on the theory we introduced on Monday, I told you that whatever this original circuit is, for the low circuit to get the maximum power consumption, RO, if it's adjustable, it needs to be adjusted to exactly RTH. Okay, I verified it yesterday on Monday. Let's look at that equation later on the notes. But you should know that how to verify it. It's on Monday's notes. Okay, it's recorded in the video. So let's use that as a conclusion. So RO has to be exactly RTH. Okay, in order to have RO consuming the maximum power. Okay, let's use this as a conclusion for now. So you are saying, hey, if I have RO exactly the same as RTH, so whenever it's consuming the maximum power, it's going to be exactly 50% of the power consumption of the circuit because it's equal to RTH. Is that correct? The question of the problem is asking what is the voltage, find the percentage of the total power developed in the circuit that is delivered to RO. Here's the circuit. So it's asking the total circuit, so the total circuit including RO is developing current, developing power, and how much of the current, how much of the power developed in the circuit is being delivered to RO. So which ones are developing power? You don't know yet. You have to use mesh current method to find out. Use the sign convention we have been using, right? A plus sign, if the current is injecting into the plus sign, it's absorbing. If it's delivering, the current is going out from that plus sign, right? You have to use current mesh method to find out which one is developing and calculate all the developed power and also calculate the power consumption of RO. Could RO by any chance developing any power? Can resistor developing power? No, resistors are always consuming, absorbing. Keep in mind, resistors are always consuming. So you get all the circuits, some of the components are developing, you add all the developed power in the circuit, add it, and then use whatever power consumed by this guy divided by that overall developed power to get out that to find out the percentage. So why it's not 50%? Why you cannot directly use this circuit? It's already changing the nature of the circuit. Why? You converted everything into this little equivalent resistor and this source. It's changing the nature of the circuit. Why you have so many other sources, like dependent sources and other things, and some of them are developing power. Some of them are consuming power. However, if you convert it to a resistor, this becomes the overall power being consumed by whatever in the original circuit. It's changing the nature of the circuit. This guy is only absorbing or consuming. It's not developing anything. Anyway, come back to the original circuit, find out which ones are developing, and then get out the ratio. That's the way to calculate the answer for problem 3, question 3, okay? All right, see you on Friday.